Module 11, the gas phase, using the ideal gas law in stoichiometry. Experiment 11.2.
The ideal gas law is a very useful law, and believe it or not, it can be applied to stoichiometry. That's because there's a value within that formula to calculate moles. We can take measurements of other parts of a material to calculate the moles of a material in a formula or within a equation, and then we can use stoichiometry to relate that number of moles to other materials in that equation. So we're going to do that today. What we need to first do is we need to measure 200 grams of vinegar. Now there's many ways you can do this. We're going to put the vinegar into a container. You can set the container straight on your mass scale and then just pour until you get 200 grams more than what you had, the original. But because it's a little bit wobbly, I'm going to use my container here that goes on the mass scale and make sure it's nice and zeroed out. So it reads 0, and then I'm going to pour 200 grams directly into this container and then transfer it to the bottle. And I will show you that just a moment. And you can see that's 200 grams of vinegar. So I'm going to use a funnel to transfer it over so it can go nicely. When you pour into a funnel, lift the funnel up. Don't let it sit on the container because you get a seal and air can't escape as you're pouring liquid in and it won't pour as well. So if you lift it up a little bit, that's a nice trick for measurement. Okay, make sure all of it goes in. Now, I'm going to do the same thing. We have to measure 30 grams at least of baking soda. So I have a different container. You can wash out your original container if you wanted to dry it and use it again. But I'm going to make sure it's zeroed again. And you want at least 30 grams. You can have a little bit more, but at least 30 grams. Well, and I have almost 50. I'm going to take a big chunk out of that. Whoops, but we'll clean that up later. Okay, so I have about 40 grams of baking soda. We need to transfer this to our balloon. You've done this in an experiment before, and I like to use my little squash corer, but you can use a knife or a funnel. Sometimes working with a funnel will work as well. What I'm doing first is I'm chopping up all the big chunks because it tends to have clumped a little bit. And then I'm going to transfer the baking soda into my balloon. It's actually good to measure out a little more than the 30 grams because you can see this is not super precise. Some of the baking soda might not make it into the balloon. So if you do a little bit more than 30 grams measurement, you know that you're going to get at least that much in your balloon. And what we're going to do next is set the balloon onto our empty bottle here that's got the vinegar inside. And make sure it's a nice tight seal because you don't want any of the gas to escape once you add your baking soda to your vinegar. Okay, once you've done that, you can go ahead and lift up the balloon so that that baking soda gets out. And I like to hold the seal just again to make sure that it stays. Shake that balloon a little bit more, make sure you get all the baking soda out that you can into the bottle. Now what's happening here is a reaction, obviously a chemical reaction. You have baking soda and vinegar that are reacting together. And the formula you have in your text, but I have it up here as well, the baking soda and vinegar. Vinegar is in a water mixture, so it's aqueous water with the vinegar. And they produce water, carbon dioxide gas, and sodium acetate. Now, this is the carbon dioxide gas plus some water vapor that we're collecting in the balloon. So we want to focus on that carbon dioxide gas. We want to know eventually how many moles of carbon dioxide gas are being produced. And to do that, we first need to measure the circumference of the balloon. Our goal is to get the radius of this balloon. So you want to get a tape measure and measure the widest part of the balloon. We're going to guesstimate this as a sphere. And if you have a tape measure with centimeter measures, that's great. If not, do the inches and we can convert to centimeters. Conversion should not be a problem. It's a little unwieldy. You may need a helper. I will try to do it myself so that I can read it. And I have, looks like 58.1 centimeters. And what we're going to do is we're going to take that number and divide it by 10 because we want that number in decimeters. So 51.1 divided by 10 is going to be 5. Let me just double check here because I always want to make sure I'm accurate. 51.1 divided by 10. Yeah, 5.11. So it's going to be in centimeters or decimeters. We have 5.11 decimeters. And actually, it needs to be 5.1 because I measured to the 10th place. All right, let me just move this balloon over here for a few minutes because now we're going to do lots of calculations. The actual experiment part of our lab is over, but the calculations based on measurements now will be happening. So we need to find out the volume of this balloon. So once you get the circumference in decimeters, we want to divide that circumference by 2 pi because what that will do is that will give us the balloon's radius because circumference is 2 pi r. So I'm going to take that 5.1 and divide it by 2 pi. You can approximate pi as 3.14. And I get 0.81, which actually will round to 0.8 because, again, I can only go to the 10th place on this one. So 0.8 is my radius. And again, that's in decimeters because that's the units I'm using right now. Okay, so now I'm going to take that radius that I just calculated. I'm going to determine the volume. The volume for a sphere is 4/3 pi r cubed. So let me go ahead and multiply that out. Pi r cubed times 4/3. Let's see here. So we have 0.8 cubed times pi times 4/3. And I get 2.1. And that answer, of course, that answer is going to be in cubic decimeters, which is the same thing as liters. So 2.1 liters is my volume of my balloon, 2.1 liters. I'm going to box that because that's an important measurement that we will be using later. We've just calculated the volume of our balloon in liters. Okay, so now what we want to do is we want to find out the pressure that's in our area. And so you need to go to a place where you can find the local pressure in your area. There are many websites you can go to that will give you the pressure. Usually it's barometric pressure and it's found in inches. If you don't have availability of that or don't know what that is, you can approximate the pressure at 1.00 atmosphere. I looked it up today. Where I am, in the location I am, today's barometric pressure is 30.47 inches. All right, so we want to take that 30.47 inches and we want to divide that by 29.92 to get our pressure. So you can see our atmospheric pressure was 30.47 inches that I received from the internet. I looked it up and I divided that by 29.92 and I got the atmospheric pressure today is 1.02 atmospheres. I'm going to go ahead and box that because pressure is another value we need. Now, the reason why atmospheric pressure is a useful value for us is the atmosphere is pushing on this balloon with equal pressure as the balloon is pushing outward. That's why the balloon is the size that it is. So that's the pressure on the inside of the balloon as well as the outside. So we have the pressure now. Okay, so now we need to know the what's going on inside. Think about what's going on inside. We have the pressure of carbon dioxide gas, but we also have vapor pressure. We have water as a component in here, as one of the products, and water has vapor pressure. So this is actually not just carbon dioxide gas in here. This is carbon dioxide plus H2O gas. We need to just have the value of the carbon dioxide. And to do that, we can determine what the vapor pressure of the air is in our environment right now. We need to know the temperature, and so I'm going to use my thermometer, which has been sitting out for a while, so it's at room temperature. And my thermometer is measuring 21, and it's actually right on the dot, 21.1, I would say now, 21.1 degrees Celsius. Okay, so now I can look at the table that's in your text, table 11.2, to determine the vapor pressure at this temperature, 21.2. I'm going to look at my table. Now the table gives you temperature values in round numbers or just to the ones place. So my measurement was 21.1. So I'm going to look at the temperature value in degrees Celsius as 21 on the table, which means the vapor pressure is 18.7 torr. 18.7 torr. I'm going to write pressure here. And I think that was, let me double check the number, 18.7 torr. Okay, that's the vapor pressure of water. That's why I put a little H2O under pressure. Okay, well now we need to convert that to atmospheres. We want to divide that number by 760.0. So 18.7 divided by 760.0. And I get 0.02. Actually, I need to go to the ones place, so I'm going to get 0.1. Okay, and I'm putting 0.1 atmospheres for my water vapor pressure. Now, what that means is we can take the pressure of the water and subtract it from the pressure of the carbon dioxide water mixture, and that will give us the pressure of just the carbon dioxide. So we're basically just subtracting 0.1 from the number. So we have 1.02 minus 0.1 . So we have 0.9. So these numbers are subtracting and we get 0.9 atmospheres, which is my carbon dioxide pressure, okay? And that's the one I really, really want. Okay, so we have, what do we have here? We have to also get the temperature. We have our temperature as 21.1 degrees Celsius, but we need to convert that to Kelvin because when we use the ideal gas law, we have to have our value in Kelvin. Our temperature is 21. I'm going to put this up here. 21.1 degrees Celsius, and to convert that to Kelvin, all we have to do is add 273.15. So let me do that. 21.1 plus 273.15, and we get 294.25, which I'm going to round to the tenths place. 294.3 Kelvin. Okay, so this is our ambient temperature in the environment we're in right now. All right, so what do we have? We have the volume of our carbon dioxide gas, we have the pressure of our carbon dioxide gas, and we have the temperature of our carbon dioxide gas. We now can use the ideal gas law and that R value, which is a given, to calculate the number of moles of carbon dioxide that we have. So let me fill in. PV equals nRT, which is our formula. And solving for N, which is what we're looking for, N equals PV divided by RT. So our pressure value is 0.9 atmospheres. Our volume, 2.1 liters. Divided by our R value, which is a given, 0.0821 liters atmosphere divided by moles Kelvin. Okay, and then our last value is the temperature, which we calculated as 294.3. I'm sorry, 294.3 Kelvin. All right, let's run those numbers to find the number of moles. 0.9 times 2.1, 21, 294.3. Okay, we will round our number to the tenths place, and I have 0.1 moles. 0.1 moles. And I know that that's moles because, again, let's look at the units of our constant. The liters will cancel. The atmospheres will cancel. My Kelvin, which is the denominator here, will cancel with the Kelvin here in the numerator within this denominator value. And I'm left with moles. And so I know that I've got my position of all of my values correct, and I have this many moles of carbon dioxide. Okay, we're almost done. We want to know how much of the baking soda, which is a solid, how many moles of the baking soda we used. Okay, so what we're looking at, let's look at the formula here. Baking soda is this right here, NaHCO3, and there's, you'll notice there's a 1-to-1 baking soda to carbon dioxide ratio, 1 mole to 1 mole ratio. So that means that there's 0.1 moles of carbon dioxide. There's also going to be, we used 0.1 moles of baking soda, NaHCO3. So we just did stoichiometry. Now how many grams is that? Well, all we need to do is take the molecular mass of this. And actually, I'm sorry, we should be using acetic acid. I was not reading the right. So we are going to stoichiometry, not baking soda, but how much acetic acid. And again, either way, it's a 1-to-1 ratio. So that would also be 0.1 moles of acetic acid. Just did a double stoichiometry. That was a bonus for you. And that's why we need to keep referring to the steps in our labs to make sure that we're following what we're supposed to be finding out. Okay, so we need to find out how many grams of acetic acid were used as one of the reactants in this equation. And so we take the molecular mass of acetic acid, which is 60.0 AMU, atomic mass units, and multiply by the number of moles. And so I'll take the 60.0 times 0.1 and I get 6. So what that means is 6 grams of acetic acid were used in this reaction to react with the baking soda. 6 grams of acetic acid. Now we used 200 grams of the vinegar solution, but it was a diluted solution. The actual acetic acid, which is in vinegar, we used 6 grams of that. So you can see from all of this mess that we did here and all of the calculations that we did, we can use the ideal gas law to help us identify moles of a material we're using in a chemical reaction and use stoichiometry then to know how many moles of other reactants or products that are in that reaction.
In the previous experiment, you did a long series of math problems, but think about the big picture. You measured the pressure, volume, and temperature of a gas. Then you could calculate the number of moles of that gas. That let you use stoichiometry to learn more about the other materials that were in the reaction. This was an exercise to help you see that these problems you are given in your text are really for a purpose. Chemists use these processes in real life to learn more about unknown substances. Let's look at a more textbook problem. One way that hydrogen gas can be produced commercially is to react a strong acid with a metal in the equation 2-hydrochloric acid aqueous plus zinc solid produces hydrogen gas plus zinc 2-chloride aqueous. If 512 grams of hydrochloric acid are reacted with excess zinc at a temperature of 24 degrees Celsius and a pressure of 0.95 atmospheres, what volume of hydrogen gas will be produced? We know that zinc is in excess, so our limiting reactant is hydrochloric acid, meaning that all of it will be used up. We need to find out how much product is made. So we need to figure out the moles of hydrochloric acid. Then we can use stoichiometry to find moles of hydrogen gas. Then once we have moles of hydrogen, we can use the ideal gas law, or equation 1112, to find its volume. That's our plan. Converting grams hydrochloric acid to moles, we take the 512 grams we are given and multiply it by a conversion relationship of 36.5 grams hydrochloric acid equals 1 mole of hydrochloric acid. That gives us 14.0 moles hydrochloric acid. Now we can use stoichiometry to determine how many moles of hydrogen gas we will produce. Taking the 14 moles of hydrochloric acid and multiplying it by the relationship of 2 moles hydrochloric acid equals 1 mole of hydrogen, we get 7.00 moles of hydrogen produced. Our problem asks us for volume of hydrogen gas. We're given the temperature, pressure, and have moles, so we can calculate the volume with the ideal gas law. Let's rearrange the equation to solve for volume, and we have V equals nRT divided by P. Now before we plug in our values, let's make sure we have the proper units. Pressure is in atmospheres, which is good, but we need to convert our Celsius temperature to Kelvin. Adding 24 degrees Celsius plus 273.15, we get 297 Kelvin. Plugging our answers in and canceling out units, we end up with 180 liters of gas were produced. And that's our answer. Let's try another one. To make magnesium hydroxide a major component in stomach antacids, hot water vapor is passed over solid magnesium in this equation. 2H2O gas plus magnesium solid produces magnesium hydroxide solid plus hydrogen gas. If 4.50 liters of water vapor at 200.0 degrees Celsius and 4.94 atmospheres are passed over excess magnesium, how many grams of magnesium hydroxide will be produced? Let's plan our strategy. We're given the amount of the limiting reactant in excess magnesium. We need to find out how many grams of a product are made. We have liters, temperature, and pressure of the water vapor, so we can use the ideal gas law to calculate how many moles of water that is. Then we can use stoichiometry to find out how many moles of magnesium hydroxide are produced, and finally convert moles of magnesium hydroxide to grams magnesium hydroxide. To begin, we need to rearrange the ideal gas law to solve for moles, so we get N equals PV over RT. Now before we plug in our values, let's make sure we have the proper units. We have liters for volume and atmospheres for pressure, but we need to convert Celsius to Kelvin for temperature. That would be 473.2 Kelvin. Now we can put our values here. Canceling out units and multiplying and dividing, we get 0.572 moles of water. Now we can use stoichiometry to determine how many moles of magnesium hydroxide are produced. We have 0.572 moles of water and can multiply it by the relationship of 2 moles of water equals 1 mole magnesium hydroxide. Canceling out units and multiplying through, we get 0.286 moles magnesium hydroxide are produced. Our problem asks us for grams of magnesium hydroxide, so we have one more step. Let's take that 0.286 moles and multiply it by the relationship of 58.3 grams of magnesium hydroxide equals 1 mole magnesium hydroxide. Canceling out units and multiplying through, we get 16.7 grams magnesium hydroxide are produced.
Believe it or not, we've spent an entire module studying the gas phase. But remember, most of what we've talked about deals with gases that are ideal. How do chemists handle non-ideal gases? Well, that's for a much more advanced chemistry course. We know that gases behave ideally when the pressure is near or below standard pressure and the temperature is near or above standard temperature. These two parameters are pretty close to room temperature and pressure, so most of the gases that you come in contact with will behave in an ideal manner.